I'm all set. Thank you. And I also want to thank Jay and the rest of the organizing committee for inviting me to come here. I'm really excited to be here. I actually haven't been to the University of Illinois before. It's my first trip, so I'm anxious to visit and see what it's like here. So yes, I'm from Ford, and this talk is going to be a lot different than every talk that you've seen so far because I'm an industry guy and not an academic guy. So I'm going to have some equations and stuff, so you won't get too bored maybe, but it's not going to be as in-depth and theoretical as many of the other talks that you've seen. Hopefully you won't be bored. My talk is going to be in 3 parts. The first part is going to be about automotive control engineering in general, how we do control systems development within the company. And I'm going to go over a lot of the things that are important to consider when you develop a control system. From there, I'm going to go into the second portion of the talk. The second and third portions are both focused on a particular case study, if you will, within automotive controls, specifically in hybrid vehicles, the problem of energy management within the vehicle, that is balancing the use of the motor and the gas engine in the vehicle. I'm going to first talk about the problem in general, what I call here the degree of freedom analysis. And then from there, I'm going to talk about 4 different ongoing collaborations we have with different universities at Clemson, Michigan Ann Arbor, Michigan Dearborn, and MIT. So I'll go into those in quite a bit of detail. OK, so the first part, automotive controls engineering. So I like to motivate this part by telling a little story about a time when I was sitting at Ford with my boss, and we just finished reviewing one of our projects that we have ongoing with one of our university collaborators. And they'd done some really great work, and I was very excited about it. And I thought, this is great. And so to my boss, I said, how come it's so hard to implement this stuff in the vehicle? I mean, they've done this great work and these great results. Why can't we get this in the vehicle and get it to work? And he said, because they do engineering in the small. And so I need to qualify this first by saying that he used to be a university professor himself for maybe 10 years or so before joining Ford, so maybe he's qualified to say that. So well, what do you mean? So we talked about it a little bit, and I think it boils down to this. So when you're designing a control system in an academic sense, you think about the system, and you think about what are you trying to control, and you have some kind of a plant, right? So what do? You model that plant, and then you design your control system for that plant, and then you implement it, probably in simulation, and then you test it, see if it works, right? And that's it. Well, that part of the process fits right there within our control system development process. So that's what I mean by engineering the small. That's only just a little bit of what we need to do to get controls within the vehicle. Okay? So I'm going to go through different parts of this process and what's important about this today. So what is the big picture? Well, there's a lot of things that you need to think about when you're developing a control system for a vehicle. It all starts with requirements. You need to understand, well, what does this thing need to do? What is important? So obviously, when you're developing cars, you have a huge, broad customer base. There's people that drive our cars in the northern reaches of Canada all the way to Death Valley, and that's just North America, right? And there's all different kinds of environments they operate in. So you need to satisfy all of their different kinds of requirements. Cost is critical, right? We're not Rolls-Royce. We're a Ford Motor Company. So we need to watch our pennies. We can't deliver a car that's too costly. So we need to always be pushing cost out of the car, and that includes in the control system as well. Complexity is everywhere, and that's not just within the car. The cars are very complex these days. You may not have an appreciation for it. I mean, you just generally get in and you drive it, and it works generally fine. But what's within the vehicle today is incredibly complex, and I'll show you some of that later. But there's also a lot of complexity in other aspects of my work, like the organizational complexity. So I work at a very big company. And there's organizations within Ford that are responsible for powertrain controls, chassis controls, active safety controls, body electronics, brake controls. And that's just within the company. And then you got all of the suppliers delivering their controls to our vehicles. So it's a huge organization that all needs to be marshaled together to deliver these things. I guess I maybe covered last, but a little bit. The many systems are delivered by suppliers, and they all have their own intellectual property and their own designs that they need to maintain and get to work in the vehicle. And Ford needs to be the system integrator for all of that. So that's complex, too. I sort of alluded to this already. The vehicles must work in all operating conditions. In as cold as you can imagine, as warm as you can imagine, at the top of Pikes Peak, in the humidity of Florida, anything you can imagine, it needs to work, right? And in almost every use case. We often get videos, sort of YouTube videos that go through the company that show people using their cars in ways that you could have never imagined they would use a car, and the car needs to still work. Right? Customers demand refinement across all vehicle attributes. This is going to be an important part of my talk. So you can't just design a control system to solve one problem in the car, because invariably that means you've broken something somewhere else. Okay, so you need to get everything to work together and deliver a total refined vehicle. So you need to think about that. And then finally, safety and quality are absolutely the minimum cost of entry. All right, so let's start with requirements. What this plot shows is actually some real data from our production engine controls group from 2006 to 8. They track their defects within their control strategy whenever they get them back. So normally, they hand over their control strategy to the people who are doing the vehicle development, and they're testing the vehicle and calibrating the control system, and they find problems. Or worse yet, maybe the problem will get into the market, and a customer will find a problem, and they'll come back, and we'll find a defect that way. But in any case, they do have defects. Everybody has defects, and they track that. And you might be surprised to learn that the biggest defects come from misunderstood requirements. So they don't know exactly what the control system is supposed to do, either because it was not properly cascaded by the vehicle engineering team, who are trying to tell all the subsystem what they're doing, or maybe the controls team just didn't understand it properly. Okay, so understanding exactly what the control system needs to do is a big part of the work. These requirements come from many different places. Okay, obviously safety is a big requirement. I hate to pick on our competitors, but of course you've seen the information about Toyota recently with the unintended acceleration. So there's no indication that that's a controls problem in their vehicles. At least nobody has said that yet. But there is a controls aspect to that situation in the vehicle. So all vehicles in the US, I think now, or nearly all vehicles, are drive-by-wire, which means in the sense of accelerator pedal. So when you step on the accelerator pedal, it's not connected to the engine anymore. It's connected to a sensor, and then the sensor the sensor's connected to the computer, and the computer decides what the vehicle should do. Okay, so you can imagine lots of different failures there, where you step on the pedal and the computer decides you're going to do something else, right? If you don't have your control system developed properly, so that's a huge requirement. But there's all kinds of other requirements as well. There's customer requirements, and you can think of some obvious ones. Well, of course, like fuel economy or performance 0 to 60 time, but what about sound at the driver's ear? You think, well, how does that relate to a control system? Well, the driver hears the engine going up and down in speed, and if you control the engine in a way that it sounds terrible, the driver's going to hear it, and they're going to wonder what's wrong with my car. Right? So you need to make sure that you control it in a way that is not objectionable from an NVH or noise, vibration, harshness standpoint. Regulatory requirements. Okay, of course, there's emissions requirements and electromagnetic compatibility requirements. I threw another one up here, headlight intensity. How could control system possibly impact the headlight intensity? So this is one that's come up recently in some of our stop-start vehicle applications. When the engine shuts off in a vehicle that doesn't have a high-voltage battery, there's no alternator charging the battery anymore. And if you don't control that properly, you could dip the battery voltage, and then the headlights dim, and that's a regulatory requirement that you can't do that. Okay, so control systems impact a lot of different things. And one last point, many of them are conflicting. So you might try and satisfy one controls requirement, and it may hurt something else. So you need to manage these well, and you can't underestimate the importance of that. Okay, the next thing I'm going to talk about is complexity. Right, this is a chart that shows our existing today, the control electrical architecture in our vehicles. Okay, so each one of those boxes, I know you can't read them, but each one of those is an embedded control module within our vehicle. There's 3 primary networks here: a medium-speed control area network, or CAN bus, high-speed bus, and then actually a number of LIN buses. But each of those is a module, each with its control code in it, each running some different part of the vehicle, and they all need to be coordinated together. Okay, so that's some of the complexity in the vehicle I was talking about. In order to see how those communicate and the complexity there, this is the growth of the number of signals back and forth across all of these buses by year. So here we are in 2010. We have almost 2,000 signals going back and forth across those buses. Okay. Just to give you an idea, if you're just picking on one module, this one you can't read, but it's the powertrain control module, so the engine control module. If you just look at what's inside there, we organize the functions and try and, we have to understand it at a functional level, and we keep track of each of those functions, what their inputs and outputs of those functions are, like any control system. So here's just a snapshot of looking at some of those functions in there. Just to pick on one, here's estimate lateral vehicle speed. So you need to know how fast the vehicle's moving sideways if you're doing some kind of vehicle stability control. It has 4 inputs and 1 output. Okay, and the rest of these are other functions like that, and you can sort of back out of this diagram a little bit, and you see some of those. Okay, and so that's the collection within that module of just the vehicle control functions, not the engine control. That's not the spark control and the fuel and so on. That's just the vehicles at the high level stuff. That's about 20% of the module. Okay, and so far I'm showing you a connection between those functions, but if I show you the connection, this is what it looks like. So it's extremely complex. Okay, that's my point. It's very complex, and you need to manage that. Okay, and then one last bit about complexity is if you look at the number of software lines of code, here we are at 2010. Within Ford Motor Company, we have about 10 million lines of code within the vehicle. The industry projection is that we're going to go up to about 50 million lines in the next few years. Okay, and we're already designing these vehicles, so this is not too far off of a projection. Okay. So the way we handle that complexity is by managing the architecture. This is one look at the architecture. This is what we consider part of our electrical architecture. Of course, there's a mechanical architecture in a vehicle. That's how do you connect the engine to the transmission to the chassis and so on. But what's really important to me as a controls person is the functional architecture. And by this, what I mean is how do we take different functions in the vehicle and organize them and manage their relationships. So I've just shown you a few here. Within the engine control module, the transmission module, and the brake module, we have some very, very high-level functions. We have some vehicle controls that's managing the torque within the engine. Then we have some engine control software. Within the transmission, we have some things that are managing the ratio. That is sort of the ratio through the transmission. And then we have some lower-level trans control software controlling clutches and line pressures and so on. And then similar over here for brakes, we have a couple different levels of control. And we have to manage all of these interfaces between them. And it's very important for us to do that in order to make sure that we don't have competing control between these modules and between these functions, right? It's not just enough to manage it at this level, though. We have to go down even further. So if you look within these boxes A, B, C, D, E, and F, we actually go into more detail further down. And this just shows the primary signals within those boxes and the primary functions. But we manage it at that level as well. And we have to sort of manage it at all these different levels in order to make sure that we can keep control of all of this complexity within the vehicle. Okay. So by managing this architecture, it really gives us a lot of benefits. It gives us benefits in terms of portability and reusability, which then result in cost savings and faster time to delivery. And obviously, those things are very important in the marketplace. Okay. What are some other challenges we have? Implementation constraints. Okay, I mentioned cost. That cost is critical, especially for a company like Ford. We don't have the advantage of your desktop PC to implement these controls in. We have something much cheaper and much less powerful. Again, I like to pick on the powertrain control module. You can see a picture over here. The cost for that kind of a device is less than $200, I'd say much less, maybe closer to $100. And this is the kind of performance that we get. We have a 56 megahertz processor, 2.5 megabits of RAM. Okay, how big a hard drive do you have on your computer now? Right, it's 2.5 megabits. 32K of RAM, internal to another 65K external to the chip. And of that, only 32K is keep alive, which means when you turn the key off, the information stays in there. The 65K goes away when you turn the key off. And if you disconnect the battery, it all goes away. It has multiple task rates running in it. So it might have tasks that are running at 100 milliseconds, 50 milliseconds, 30 milliseconds. In the powertrain module, it goes down about 8 milliseconds. Some of our other modules have faster loop times. And there's about 500,000 lines of code or so in that module today. So that's one constraint, is that that's the computing platform that we're working with, okay, for that particular subsystem. But we have a lot of other constraints as well in terms of sensors and actuators. Obviously, again, cost, but also packaging. You can't put a torque sensor. At least you hadn't been able to. There are recent developments on that are looking pretty good. But you can't put a torque sensor right on the engine because it can't operate in that kind of a environment with hot transmission fluid flying around it. And of course, we always want to have complexity reduction, so we don't want to add more sensors to the vehicle because it just makes things even more complex and harder to manage. So we're trying to get rid of them rather than add them. And then finally, another challenge with controls in the vehicle is that we have distributed control. I showed you that diagram with all the modules. Well, many functions within the vehicle span modules. That is, you need to have some function running in the engine control cooperating with some function running in the brake control to ultimately deliver that vehicle control function. Okay, and so the way we do that is across these networks, like the control area network, which runs at about 500 megabits per second. Okay. I alluded to this already, that you can't just solve one problem in the vehicle. You need to be attentive to what's going on in the entire vehicle. So if you look to develop a control system that will solve fuel economy, for instance, very likely it'll have a negative impact on drivability or vehicle performance. So you need to be thinking about all the different vehicle attributes that customers care about and think, how is this control system that I'm designing going to solve all of these at once? Okay, or is it going to be detrimental to something that I'm designing? So just to give you an example, and this is why I'm picking on myself here because this is going to be in the later half of the talk, we often look at fuel economy and say, well, what we want to do is minimize some kind of a performance index here, which is the mass of the fuel summed across the whole trip. Okay, so if we're going from here to Chicago, we want to use the least fuel possible. So we're going to sum that up and try and minimize it. So we want to develop a control system that'll do that. But like I said, if we don't consider other attributes, they may have a negative effect. Some work we're doing with the University of Michigan and Dan Apilla, which I'll talk more about later, actually goes after that problem. Whereas in a typical design, you might design this separate from this and then have negative impacts later. He's doing a concurrent design where he takes into account drivability considerations along with energy management considerations, and then comes out with a single controller. So you can see here, I'll talk a lot more about this later, but he has engine events here and gear events here, which are some measures of drivability, and fuel economy here. And he has a whole range of controllers, a whole surface, if you will. And if you tell him, hey, I need drivability that meets this metric, and I want fuel economy this metric, he can tell you whether you can achieve that based on whether you lie on that surface or not. Okay. All right, just about done with the first part here. Calibration is another challenge for us. So calibration is a term that's used in the auto industry, and I didn't know what it was when I got there, but it's just tuning your control parameters. Okay, that's what it means. And it's a whole cottage industry within the automotive industry. There's a whole group of people called calibrators, and they got their own lifestyle, and they go on calibration trips and take vehicles home overnight and do all kinds of fun things. But their job is to play with the control system and tune it up until you've met all of those attributes, right? The drivability, fuel economy, all those attributes. So these people are not generally controls engineers. They're more like vehicle development engineers. They know about vehicle requirements. They know how they have very sensitive backsides, and they can tell what good drivability is and what bad drivability is just by driving the vehicle. And so they're good at that. And they need to be able to have knobs, if you will, that they can turn in order to meet those attributes. So they need a control system that has enough tunable parameters in it. So our current control system in the engine, just in the engine, has about 6,000 parameters for them to tune. Okay. Before we deliver a vehicle and launch it, we need to have tuned all of those parameters. Okay. So let me give you an example of something that doesn't really work. Think about LQG, where you have some kind of performance index, where you have some weighting functions, F, Q, R, right? You design your LQG controller, and you set those, and you come up with some control that balances your states versus your control input. I think if you showed that to a calibrator, you'd say, what the hell is F, Q, and R anyway? And what does it mean if I set Q to 3,000? What does that mean? Okay, so they need to have something that's relatable to the vehicle, so they can tune a parameter and see the response in the vehicle, and they know if they turn it into a little bit more, it's going to respond this way. Just to give you one example about how just one small success story, about how we've done some good work from the control side to help our calibrators recently, a couple years ago. We were developing a hybrid vehicle, and so hybrid vehicles come to a stop when the vehicle stops. The engine comes to a stop when the vehicle stops. And we had the control system developed, and they were just doing the initial vehicle development and calibration. And they didn't know exactly how often the engine should stop, what conditions they should tune it to so the engine shuts off at the right points. So we did a simulation where we maximized the fuel economy in the simulation over a particular drive cycle. And then we gave those response characteristics to the calibration team. You can barely see it here, but I guess let's see. This one's a simulation in the little green spots here where the engine shuts off. And they were able to use that then to guide them and try and get the vehicle to shut off by tuning the calibration parameters. in the same way and thereby maximize the fuel economy in the vehicle in the same way it was maximized in the simulation. So they were able to get about 33% improvement in the engine, or sorry, 33% engine on time versus a target of 34%. So that was actually a small success story. So you need to be, the point is, you need to be thinking about the calibrators. Okay, how are they going to do it? Okay, I mentioned it needs to work in all regions. So there are many noise factors that can impact your control system. Some are environmental factors. Of course, you think about rain and snow, and of course, that stuff might be obvious. But you also need to think about electromagnetic interference and compatibility. You need to think about altitude, humidity, vibration, fuel quality. Any kind of noise factor you can think that might be out of the ordinary can impact your vehicle, and therefore your control system needs to be able to handle it. You also need to think about customer usage profiles, or customer usage use cases. So normally people get in the vehicle, they turn the car on, they put it in gear, they drive away. That's a normal use case. But there's many other things people can do. And so I mentioned here accidents. I don't mean accidents in the case that they run into the vehicle ahead of them. I mean accidents that they spill their Coke on the accelerator pedal. And now what happens? Okay, so you had this sensor there, which was a critical component between you and the engine power. And if you spill your Coke on the accelerator pedal and it gets in that sensor, does the vehicle suddenly accelerate? So you need to think about all of this stuff. You know, what can possibly go wrong, and how do you make sure that if it goes wrong, it doesn't cause a dramatic failure? So the way we do this is by using a lot of failure avoidance and mitigation strategies, thinking about all the things that could possibly go wrong, making a plan for what we're going to do if they go wrong, incorporating that into the control strategy, and then verifying through testing. All right, last bit on the first part is this testing aspect. So once we've developed the control system, it's not enough to just check it in one simulation. It has to go through an extensive set of validation to make sure it works under all cases, okay, and does exactly what we think it does. So the way we do that is we take our control model and couple it with a plant model and do simulation testing like you'd imagine. We also then turn that control model into code and put it into our embedded module. And then we couple it to something called a hill system, a hardware-in-the-loop system, which is like a powerful computer where we can run real-time, run our plant model in real time so it can keep up with the actual production module. And then, of course, finally, we take that production module out of the hill system and plop it in the vehicle and do our testing there as well. All right, so let's wrap up. What did we learn here? So requirements are important. We have a whole part of our process up here focused on making sure we understand the requirements. We take them from the vehicle level, cascade them to the control level. Complexity. We need to make sure we don't get overly complex, so we do that by managing architecture. And then we also need to make sure that we can implement in a real production module under the constraints that we have. Robustness to noise factors. We have a whole section in our process up here, including the driver. Validation. This whole portion is focused on validation. And then finally, verifying the vehicle attributes. That is across all the attributes, not just, say, fuel economy. And calibration, right? So that's all part of the process. All right, so that's the intro. So now let's go into this case study. So keep in mind everything we've talked about so far, but what's important in terms of designing a control system. So I'm going to talk about what the problem is, and then I'm going to talk about what these 4 different universities have done to try and solve the problem, and we're going to think about it a little bit in that context of our process. Okay. So first, let me give you a little background about what the problem is. You may know more or less about hybrid vehicles, but I just want to give you some grounding as to how hybrid vehicles, why they produce better fuel economy. There's 4 things, really, 4 factors. One is that you can downsize the engine. So a hybrid vehicle normally has a motor, an electric motor, or 2, and a gasoline engine. Conventional vehicle generally only has an engine. So if you have a conventional vehicle, you have to size the engine for maximum acceleration. So the 0 to 60 time, you have a certain weight of vehicle, you need to have a certain size engine to go that fast. Okay, that's how you decide the size of the engine. Well, so that's this operation up here. This is torque versus speed of an engine. So it's operating up here during maximum acceleration. But most of the time, it's operating down here because you're not normally shooting off the line or anything. So you're down here operating. And the problem is, this is the most efficient operation of the engine up here. So you're operating at less than efficient operation. So with a hybrid vehicle, what you do is you make the engine smaller, and when you need that extra boost, you use the electric motor. So most of the time, the engine's operating in the sweet spot. And if you need more power, use the motor. Okay, another benefit is regen braking. So this is when you're decelerating. Normally, you burn up all that energy in the friction brakes. But in this case, you have this motor that's coupled to the wheels. So you can apply a negative torque, and it funnels energy back into the battery to use that energy later to drive the vehicle with electrically. Okay, so that's a sort of a freebie. engine stop start. When the vehicle comes to a stop, the engine, normally in a conventional vehicle, the engine is running away and you're just burning up fuel while you're sitting there. So you shut the engine off, and then you use electric motor to start it up quick when you drive away. So that's stop start. And then finally, energy management. This is the problem I'm going to talk more about. So here, this is a little bit more complicated. What you're trying to do is when the engine's on, you want it to run in the sweet spot, right, in the most efficient spot. But you might still, when you're on, you might not quite be there based on just what the driver's demanding in terms of the acceleration of the vehicle. So you can move the engine's operation into the sweet spot by accommodating the extra torque that's required or not required with the motor. So you're either funneling energy into the battery or out of the battery with the motor in order to push the engine back into its most efficient operating region. That's the energy management problem. Okay, so let's go in a little more detail into that. This is the system diagram for our power split HEV system, which is the system we worked on most. It's a system we have in production in 4 different vehicles. It has, the center of it is this planetary gear set. And connected to that on one side is the engine to the carrier. Connected to the sun gear is the generator. And connected to the ring gear through some other gears is the motor. So this has 2 electric motors in it. And don't be fooled by generator and motor. They both can operate either with positive torque or negative torque. Okay. The motor is also coupled to the wheels through some other gears. Okay, so that's the system. Of course, you can draw a free body diagram of that and then write down the corresponding governing equations where you have accelerations of the masses and you have some kinematic speed and power relationships and then some loss terms. Okay. For the energy management problem, that's a pretty slow problem, so you can ignore these fast dynamics of the different the motors in the engines, at least the first order. And so then you come up with some steady state operation. You move all these, you convert all these equations here, and you basically have 8 equations with 12 unknowns. Okay, 2 of those unknowns are constrained though, because the driver demanded torque, so what the driver is asking for at the wheels, as well as the vehicle speed are given. So then you can reduce it down to 10 unknowns. So you're left with 2 degrees of freedom. So 2 independent variables that you can move around to choose the engine speed, the motor speed, the generator speed, the motor torque, generator torque, battery power. Pick 2, you get 2. Okay? And what you're trying to do here, what these charts show, is that you have engine torque and speed, and these lines are lines of constant efficiency. Same thing here, motor or generator torque and speed, motor torque and speed, lines of constant efficiency. And this is battery efficiency versus battery power for lines of constant state of charge. So you have all of these different devices, each with their own efficiency, and you're trying to push these devices around into an operating region such that the total efficiency is maximized. Okay, so that's the energy management problem. Everybody got it? All right. Okay, so now let me give you one little other piece of background. This is what I think when I was introduced, I said I work on vehicle controls. And so let me tell you what vehicle controls are. Vehicle controls are the portion of the control system that take the accelerator pedal, brake pedal, and other driver inputs in, interpret what the driver wants from those, figure out the best way to deliver that, and then command that to the subsystems. So coming out of here are the friction torque requests to the brakes, the engine torque command to the engine, the motor and generator torques, and so on. So this is doing all the coordination control of all the different devices. All right. This vehicle controls for this problem, for the energy management problem, can be further split up into 2 parts. One is the independent parameter calculation, and one is dependent parameter or variable calculation. Okay, so this is calculating those 2 degrees of freedom. How do you want to choose those? And once you've chosen those, then the rest is determined because it's constrained that way, right? So you can choose, like I said, you can choose any 2 you want. I just happen to write on this page battery power and engine speed, but any 2 of those variables you can choose. Okay, so now let's define our problem a little further. What we're trying to do here is maximize the fuel economy over a given drive cycle. So in other words, we have a performance index here where we're going from sometime 0 to t, which is our length of our drive cycle in time. And we have some fuel usage that we're integrating over time, and we want to choose the value of u, which is our 2 independent variables, such that this whole performance index is minimized. We're also constrained in that the battery state of charge at the end of the trip has to be the same at the beginning of the trip, because otherwise we're just using the free energy in the battery and we're left with nothing in there, and it makes us look like our fuel economy is really good, but we've just used up all the battery energy. So you've got to have the same energy in the battery at the beginning at the end as you had in the beginning. And of course, we're constrained by a number of things, all the different torque limits and speed limits of all the different devices in the system, right? So if you want to see what opportunity exists here, okay? So we have an energy management strategy in our vehicle now. We have vehicles in production. We have them in production for 5 years already. So there's something doing there. We're choosing these parameters somehow, right? But is there any opportunity to do better than what we have in our vehicle today? And so one way to do that is, well, let's apply dynamic programming here offline, and we'll see what the best we could possibly do is, and compare that to what we have today and see if there's any opportunity. Okay, because if we already got the best, then let's work on the problem and go do something else. So if we apply dynamic programming, again, just pick two of the variables, pick battery power and engine speed. Assume we know the states at the beginning and the end of the cycle, okay, because when you get in, the engine's off, so you know that state. And when you get out, the engine's off, so you know that state. And you assume you know the driver's input in the whole drive cycle. So you know that I'm going to drive to Chicago, and I know exactly how fast I'm going to go the whole way. Okay, so obviously, we don't know that in the real vehicle, but for offline, we can make that assumption. And then just pick the sequence of states that's going to minimize this performance index. And so for dynamic programming, we just step backwards in time, picking the best state at any given time, and then we calculate a cost to go and so on. I think probably most of you have been exposed to that, so I won't go into too much detail there. So here's the results for our escape. We have a base simulation, which is just a simulation model that emulates what our vehicle does today, our actual production escape hybrid. And we've run DP on that. And this is the drive trace, the vehicle speed trace that we're trying to follow. So this is a prescribed government trace that you measure fuel economy on. And you can see we've been able to choose a set of variable choices that allow us to follow that drive cycle. Okay, so that's the first challenge. Can you pick a set of battery power and engine speed such that you actually do follow the drive cycle? You have to follow that, otherwise you don't have a valid run. So we can do that. And then here's an interesting thing. So this is the base model. Again, this emulates what's in the vehicle today. And this is the DP, and this is the state of charge of the battery. So this is an indication of how the battery power is used throughout the cycle. So if the state of charge is going up, that means you're charging the battery. And if the state of charge is going down, that means you're taking energy out of the battery. Okay? So obviously, the dynamic programming routine does something different than the base one. It's taking more energy out of the, it's charging the battery early and then using that energy later. Okay? Here's probably the most interesting part. This shows, again, the engine torque and speed. And the lines, the contour lines here are lines of constant efficiency. So the blue dots are the base case. That's, again, simulation what's in our vehicle today. And it shows all the different operating points for where the engine's torque and speed are throughout that cycle every 1 second. The red dots are what the DP is doing. Remember, up here is the most efficient region. So you can see it took a lot of points here and pushed them up there towards that efficient region. So there's some opportunity there, right? Very interesting. So, interesting, but okay, the DP results are not readily realizable because I had to calculate them all backwards in time. I had to know the whole drive cycle. It's not computationally efficient. I didn't mention this, but to run that one cycle on a pretty powerful desktop PC, it took 3 days just to run that one 1400 second cycle. Okay, and of course, think back to my earlier portion of the talk. We didn't consider any other attributes, right? We didn't think about how it impacts drivability, so it could just blow up the drivability. All right, so let's do a little grading of how we did against some of our objectives for our control system development process. So in terms of requirements, well, we're trying to go after fuel economy. That's a big, important requirement for us. So C, okay. Architecture, we did a good job there because we isolated the 2 independent parameters from the rest of the control system, and we structured that in a way that if we calculate those 2 parameters, it's not going to be spaghetti code throughout the whole rest of the system. Again, nice architecture. Complexity, well, I mean, it's dynamic programming. It's all offline. It takes 3 days to run. It's pretty complex. Implementable, no. Balanced attributes, no. Didn't consider anything else. Robust, well, no. If the drive cycle changes, then all your results are off. So got Fs for all of those. I didn't even grade calibratable and validated because we haven't implemented it. So far, just engineering in the small still. All right. Okay, let's go on to the next part. So let's see if the university guys have done any better. They have. Okay. Okay. All right. So our first one I'm going to talk about, and let me just say, on all of these it says collaboration with Clemson University or collaboration with whoever. I mean, they're doing the work, and I'm just taking credit for it. So this is really a lot of university work that is very good, and we participate with them sort of on a monthly basis. They're doing the work, but we're just sort of giving them guidance, right? So it's really their work I'm presenting. This one is with Professor Ardalan Vahidi and student Ali Borhan, who's actually at Ford today even, visiting us. But the idea here is to use model predictive control in that power split HEV. So here now, what this is, if you remember that optimization block where we're choosing those two independent variables earlier, so I'd split the vehicle controls into two parts, which was the dependent variable and the independent variable. We're going to take this MPC block and plop it into that optimization block to calculate those two variables. So coming out of here are those two variables to their low-level dependent variable calculation. But this looks very much like what it looked like before in that we have some kind of optimization routine, calculating dependent variables, and running some internal models. We're taking that whole simulation, if you will, and throwing it into the controller. The idea here is that we develop some kind of internal model that we can run in real time and do our optimization in real time and calculate our independent variables and check that, okay, in real time. In this case, they happen to choose engine torque, engine speed, so they picked two different variables. So it looks like this. They chose engine torque and engine speed. Of course, they're measuring the output is fuel usage and state of charge. We need to keep track of all the torques to make sure that because they're constrained, and we make sure we don't exceed any constraints. The internal model we've chosen is very simple. It's just vehicle speed and state of charge, because we can't run anything too complex in real time. And then we're assuming that the driver input is known. This is a big assumption. So obviously, I'm looking for things that can be implemented here in real time in the real vehicle. Okay, so we're assuming the driver's input is known. Okay, so that's not too good. But what they're doing is they're assuming some kind of an exponential decay in the driver's input torque. Because if you assume it's constant torque, you just keep accelerating. So they're assuming some kind of current torque and then exponential decay. So the first try that they had, and this went on for quite a while, they defined their performance index like this. So they have the fuel usage and the state of charge. Remember, you said you got to keep the state of charge sort of close to the nominal, because if you get too far away, you're just using energy in the battery. It's not really a fair comparison. And then they just minimize that performance index. The problem with this one, though, it didn't work. And the problem is that you don't want to minimize fuel over that short little time, delta t. So delta t here, I didn't point that out. Delta t is the time window for which you're running this optimization. So maybe it's 3 seconds, 5 seconds, 10 seconds, whatever you can fit in, whatever you have time to do the calculation where you have to run all of this stuff. But you don't want to minimize fuel over 3 seconds. Okay, and so we went back and forth and back and forth, and finally we said that doesn't work. Okay, where we're at now is they've changed their performance index so that they have an instantaneous fuel usage plus a cost-to-go term. Okay, and then they've used something which I won't go into detail, but you can find more details here, called the equivalent consumption minimization strategy, which is a sort of an alternative energy management strategy developed about 10 years ago, to calculate the value of this lambda term here. I won't go into much detail, but suffice to say, they have this cost-to-go term here, and they have this sort of neat little trick to calculate this lambda term, which seems like a magic trick. But the results are pretty good. So here, this PSAT model is the base simulation in this case. PSAT is a external modeling software from Argonne National Lab that can be used to run these kind of vehicle simulations. So they're using that because it's convenient. And then for the two different drive cycles, this is the city cycle, so like the city fuel economy number that you see on your window sticker sort of comes from this, not exactly directly from this. And then the highway cycle, the highway number sort of comes from this. And so for the base case, they get it, and ignore the absolute numbers here, about 76. Just look at the relative numbers. So the base case here is about 76 miles per gallon. And their first test was 73. So they didn't even do as well as the base PSAT case. Okay, but the second go around, they actually improved by not quite, well, I guess, I don't know, I can't calculate that fast in my head. 4%, something like that. 5%, I guess. They had an improvement using that second case. Same thing down here. A little more improvement on the highway cycle. The initial case, they did slightly better, but the second one, they did better. OK, so how did they do? I'm only looking at the 4 where we failed last time to see if they've done any better on that. Complexity, I give it a C, and that's maybe a little bit generous because it's still pretty complex. You have to have this internal model, and you can only do it a few seconds ahead of time. And if you do it anymore, it gets really complicated. So complexity and implementable sort of go together, and I generously gave him a C. Balanced attributes, I gave him an F because they're only looking at fuel economy still, so it might impact all kinds of other stuff. And robustness, I gave him a D because if they're assuming some kind of a driver profile, and if the driver profile is not at all like that, then it's not going to be robust. All right, so it's interesting, but maybe not the best. Okay, let's go to the next one. This is with the University of Michigan, Ann Arbor, with Jesse Grizzle, professor, and Dan Opila, who's a student. He's just graduating now this spring. Idea here is, okay, so we're going to improve this driver estimation a little bit. We're going to estimate the driver input using a Markov chain that says if I'm currently at a certain vehicle speed and acceleration, there's some probability that I'm going to move to some other vehicle speed or acceleration. And the way they do that is they have a whole slew of trips, vehicle trips that they have access to that they went through and analyzed, and they've just counted. Okay, if I'm at this speed, what's the likelihood I'm going to go to the next speed? They just summed it all up. Okay, and they have some kind of histogram that shows. And then on the energy management side is very similar. Okay, they have some system dynamics. They define some kind of a cost over some kind of a time frame. And then they calculate the expected value of that cost based on the instantaneous cost plus some expected value of the future cost, which depends on this Markov chain. Okay? And then, of course, the optimization of that is just choosing the minimum value viewer, the two independent variables. Okay? Here now, they're also considering for their performance index not just fuel, but gear events and engine events. So drivability is a little bit of a nebulous thing for a vehicle. I mean, I guess you get in a vehicle and you drive and you think, you sort of know whether it feels good or not, but maybe you can't really tell why it feels good or not. So we've done a lot of work to figure out what metrics we can use in the vehicle to say, to correlate to what feels good while driving. And it's pretty hard to do because, some things are like if the engine sounds bad, the person might think it's a poor driving vehicle, or if it shifts too much or shifts too little or shifts at the wrong time or shifts too harshly. So there's all kinds of different things you can imagine. So he talked to a bunch of people within Ford, that is, Dan Opila did. And the two that he narrowed it down to were gear events and engine events. So this is a different system. This one has actual step ratio transmission in it. It's not the power split system I showed you earlier. So, but he narrowed it down to these two things. So how often you shift and how often the engine goes on and off. That's the two measurements he has here. And then, of course, SOC, because of the same reason I said before. So then his cost function looks very similar to that. And this is just an indicator function that says when the gear shifts or when the engine comes on and off. And then his results are here. You can see engine events here and gear events here. And you can see the surface of different points. So if you tell him how many gear events you want and how many engine events you want, he can tell you exactly what the best fuel economy is. Okay? This is looking at it from the side, from this side here. So you can see just see the engine events looking along the gear event axis. You can see that it sort of forms this kind of a surface like this. And he's done a regression to a couple different gear event lines, 25 gear events and 75 gear events, these regression lines. Interestingly enough, too, this green dot is the Ford controller. So he's done better than our base controller. This is not for our production vehicle. This is for a particular prototype vehicle we had. And we have a specific controller that we tuned up there. And I wouldn't say it's not anywhere near production level quality, but it was not too bad. And he was able to improve it not only for different levels of drivability, but even at that same level of drivability, he was able to get about a 15% improvement there. Okay. Also, you might notice this plot here. This is engine torque versus engine speed again. And so this is the base controller, all these blue dots. And again, look at the stochastic dynamic programming. It pushes all of the operating points up closer to this maximum efficiency region. Okay, so interesting. All right, so he also looked at robustness to other drive cycles because he's got this Markov chain strategy. So what he did was he used some data from UMTRI, which is University of Michigan Transportation Research Institute. They have just oodles and oodles of drive cycle data because they instrumented a bunch of vehicles and people drove around and they took all this data and then they collected it all in this giant database. Thousands of drive trips. So he pulled out a couple different sets of 100 real-world trips out of that database and concatenated them together. And he calls them each an ensemble. And then he, in this first case, he designed the controller, so the Markov chain, with the statistics from the various drive cycles. So whether you're talking about the federal test procedure, or the New European drive cycle, or one of these two ensembles, he designed his controller using those statistics and then tested it on Ensemble 1. So designed it with FDP or NEDC or Ensemble 1 or Ensemble 2, and then tested it on Ensemble 1. So of course, the one designed on Ensemble 1, which is the black one, did the best on Ensemble 1. Makes sense. The one designed with FTP, which is our regulatory test cycle, didn't do very well on Ensemble 1. Right? So if we design a controller that works well on the federal test procedure, in this case, it didn't do very well on real-world driving. So in other words, the one we designed on the federal test procedure was not robust to real-world driving conditions. Okay? Interesting. On the other hand, when he designed, when he designed all of these controllers using these different sets of data and then tested them on the federal test procedure, look at that. They're all pretty good. So here, again, so you'd expect the one designed on the federal test procedure to be the best on the federal test procedure, and that's the red one. So it is the best slightly. But look at the ones designed on Ensemble 1 and Ensemble 2, the black and the purple. They're right up there with it. So if you use this real-world data that's pretty rich and design your controller that way, and then you test it on the federal test procedure, it actually did really well. Okay? The federal test procedure, on the other hand, is not representative of what people do in real life. Okay, so it was a real good study in robustness to different ways to model the driver. All right, so I gave him all Bs. So I was a little bit generous again on the complexity and the implementation because it's stochastic dynamic programming, and he's got this Markov chain and stuff. So it's a little bit complex, but he's done such a good job. I can't take anything away from him. Balanced attributes, of course, he looked at the drivability at the same time as fuel economy and robustness. Obviously, this is really good on robustness. So it was a little hard on him on those. He could have got A's. All right, next one. This is with the University of Michigan Dearborn, Professor Yi-Lu Murphy. And there's actually a lot of students. I didn't list them all here, but Jungmi Park is the postdoc. She's maybe the main person working on it. So this is another interesting take on the problem. Here, they're focused on neural networks. And each professor sort of has their area that they like. And so it's really fitting the problem to the solution. And this one, what's that? Solution to the problem. Solution to the problem. Yeah, thanks. And so she likes neural networks, so that's OK. So what she's doing is to take a set of, take vehicle speed and run it through a neural network and identify a roadway type. So these are some prescribed roadway types by this outfit out in California called Sierra Research. They've defined different kinds of roadway types, freeway types, arterial types, and local roadways based on vehicle speed characteristics and different levels of service. So whether if you're going like congested freeway or wide open freeway or congested arterial or wide open arterial. So she can identify to about a 90% degree of accuracy if you give her a vehicle speed what kind of roadway type you're on. Okay? This is an example of that. It's hard to read here, I know, but so here's a vehicle speed trace. And this is the actual roadway type, and this is the identified roadway type. And you can see arterial EF, arterial CD, local, arterial CD, and so on. So it identifies it pretty well based on this neural network. Then, using this roadway type, you define an energy management strategy for each roadway type. So you have another set of neural networks here, which calculate your battery power. Again, so she chose battery power and engine speed for 2 degrees of freedom. Calculate a battery power and engine speed for each roadway type based on the output of dynamic programming. So for each roadway type, she runs that through dynamic programming and comes up with a sequence of optimal battery and engine traces. So she runs the arterial A, B through the dynamic programming and comes up with a set of battery, power, and engine speed points. Then she takes that and feeds that into her neural network, trains her neural network based on those points for that roadway type and for that vehicle speed trace. Okay, so then she comes up with a set of these for each roadway type. So then she has 11 of these neural networks for each roadway type. One for 11 for engine speed, 11 for battery power. In the real implementation, you'll be driving along. It'll identify the roadway type. That gets fed in here. And then behind the roadway type, you pick one of these sets. And that'll give you, based on the other dependent variables here, that'll give you your battery power and engine speed set points. Okay, so it sort of leverages, it doesn't really predict the driver's input. but it sort of figures out what kind of driving you're doing and assumes that you're going to keep doing that. So it looks backward in time over some delta W window and says, well, the person was driving on a freeway, an open freeway there, so they're probably going to keep driving on the open freeway for a while. And then it calculates your energy management strategy based on the assumption that you're going to keep doing that for a while. And then it steps ahead in time and does that calculation again and says, well, you're probably going to keep doing that for a while. Okay, so I don't have any more details, but I can tell you right now that they've predicted improvements of about 5 to 10%. Okay, the next step is implementing the vehicle. All right, I gave them a couple of B's on complexity implementation because neural networks are pretty cheap to implement, pretty easy. They didn't look at any other attributes, and I didn't know where to put them on robustness. I put them in the middle on that one. All right, last one. This is some work we're doing with MIT, Professor Munther Dale and his student Yola Katsugiri. So this one is quite a bit different, actually. Here we're assuming we know a lot more. We assume we know the entire driver's route. So they're going from point A to point B, and we know which roads they're taking. That's a big assumption, but it may not be so bad. We use GPS and a navigation database that we have in the vehicle that tells us information about the roadway. So it assumes we know things like the total distance of the route, the expected speed along the route based on knowledge we have about the speed limits, about stop signs, stop lights, maybe traffic. And also we know the grade along the route, okay, the slope up and down of the road. Then based on this, so based on that, we calculate, or we predict a power profile, if you will, not just a speed profile, but a power profile, because we have the grade as well. And based on that power profile, then we have an energy management strategy we implement. Okay, so look at this a little more, what they're doing. You imagine you're going from point A to point B, your sort of origin to destination here. And you want to split the road into length, speed, or you have some road information about length of the route and speed information and grade information. And the idea then is to segment that route. Okay, and this is not so easy to do. But segment that route along the way where you're going to make changes in your control strategy. And then for each segment, you know the length of the segment, the average speed, the average grade, and so on. And then correspondingly the fuel used. Okay, then of course the strategy is minimize the fuel across the whole route, right? The way we're going to do that, here we're just looking at 1 degree of freedom. So we're sort of punting the other degree of freedom for now. The way we're going to do that is by picking a state of charge value, the battery. So you can think of it as battery power or state of charge is sort of equivalent, for each node here along the route. So you can imagine here I want to be here, state of charge, then here, and then here, and then here, and then up there. Finally, I'm done. Okay. So we have some sort of artificial simulations that we've done here to show you that this works. Yola developed an artificial vehicle speed profile here that has this speed profile, okay? And the grade in this first case are all 0 along each segment. And so what she did is say, okay, well, if I don't try and tweak the SOC values at each of these segment points, or these nodes, what kind of fuel economy can I get using dynamic programming? So she had a fuel consumption of 0.37 kilograms across this route. And the optimal SOC sequence was just try and keep it in the middle. You know, it wasn't trying to pre-position the SOC. It just said, you know, try and keep it in the middle. It didn't keep it at the middle. It moved around. But the target point was just keep it in the middle. If you took into account the fact that she knew something about the speed profile and used dynamic programming, she could actually get a 13.5% improvement of the fuel consumption. And this was her resultant SOC sequence. So it drove down the battery charge for a while, then it drove back up to 50. And taking into account that she's going to have this big deceleration here at the end, and she's going to be able to collect regen energy. Okay, that's where the advantage came from. So then she brought on grade information, and she said, okay, let's make the grade here non-zero. Okay, so then she ran the simulation again and said, well, if I don't have any SOC control, the fact that I have a grade now and don't know anything about that deteriorates my fuel consumption. Okay, I'm still targeting the midpoint here, but it made it worse. If I try and just use vehicle speed to set my SOC along the route, I can still do an improvement over no SOC control, even if I ignore the grade. Okay, but the improvement is lower. It's only 8% now. Now, if I know the grade, I can actually get a 3% improvement over that one as well, if I use the knowledge of the grade along the route. Okay, so there's opportunity for improvement here. But there's also many, many challenges. So, for instance, how do you segment this route? Okay, I mean, you're just driving from here to Chicago. When do you know that you want to put a segment point and put a new SOC target value along that route. Okay, it's not so obvious where you want to do that. I mean, it's based on the length of your route in total, the average speeds across the different segments, the grade changes, stop signs, traffic lights, all these things are going to impact that. So it's pretty hard to figure that out, and we're still working on that. We've also been assuming a particular speed profile across these segments. So, but you can imagine, based on different drivers or different environmental conditions, that the speed profile is going to vary, could vary dramatically, right? Maybe this is the one that we've assumed, but it could be anything, right, that gets you to that from point A to point B. And what is the robustness to that? So we're thinking, and that, of course, would change the amount of fuel used, right? So we're thinking about that. And then maybe the biggest challenge yet is trying to come up with a regression value for fuel used. So in order to run this in real time, right, maybe you're calculating this across this entire route, which is not 10 seconds. It's minutes and many minutes or hours, right? You need to have something that can run in real time all the time. And so we need some kind of regression equation for the fuel used that depends on all these other variables like the vehicle speed and the SOC and the engine speed and so on. So I would say this work is the least mature, but maybe holds some promise. Okay, and it's not so far-fetched that you might know this information, because we do have GPS in vehicles, we do have navigation systems. They don't have this data in them yet because the navigation companies haven't released that data entirely because they're still developing it. But it's not so far-fetched that we might have this kind of information, and then it's just a matter of how we make use of it. Okay, all right. So we gave them a C in complexity and implementation because there's so many details left undone yet. They only looked at fuel economy, so got an F there in robustness. They're thinking about robustness, but they haven't solved any of that problem yet. All right. So where does that leave us at the end of the day? I guess the point I want to leave you with is that successful controls application involves much more than just designing a new control algorithm, right? So there's a lot of things you need to think about. You can't just say, I'm going to minimize this performance index for fuel, because that's not going to get you anywhere. That's dynamic programming, right? You got to think about, how am I going to implement this thing? What are my real requirements? What are the affecting the other attributes? Is it robust? All of those things are important. Okay, so that's why we have this process, and that's why we use it in the company. Okay, that's it. Thank you.
How long do you think would be before they would the logic behind energy management and production vehicle?
Well, so we do have an energy management strategy in the vehicle today, right? So we have vehicles in production, and there is an energy management strategy. I didn't describe what that is, but it's simpler than this. It's more of a gain scheduling algorithm. I absolutely think we'll have these in production, and probably not that far, because on the first 3, our next step is implement in a vehicle this summer and test it. So we'll have them tested by the summer, and if it works well, we can have it in the vehicle in months from that time frame. So, yeah, go ahead. So it varied. I mean, so the opportunity that we saw by using dynamic programming, not considering grade, the opportunity we saw was on the order of about 9% over what's in our production vehicles today. Okay, but that 9% comes from a lot of, there's a lot of trade-offs, right? So it didn't consider any kind of other attributes. So there might be drivability constraints that you won't get that. There might be implementation constraints that you won't get that. So there's a lot. That's just the max possible that you could potentially get. So some of these university projects are projecting more than 9%, which I would say is not realistic, and it probably is a result of having poor models or whatever. We're pretty confident with our dynamic program results. That's sort of our ceiling that we could get. You have a question?
If you have frequent commuters, they remember what they did the day before.
Yeah, that's another way that you could anticipate the driver's speed profile. If you know, this guy gets in the car at 8 o'clock every day and he goes to work, right? So you know which route he takes, you know how fast he goes, pretty much. Yeah, you can use that information. It is cheaper than gasoline today. So everything I've talked about here is specific to, well, it's not specific to hybrids. I was focused primarily on hybrid vehicles, not plug-in hybrid vehicles or battery electric vehicles. some of this still applies to plug-in hybrid vehicles because even though you charge your battery at night from the grid, in a plug-in vehicle, you'll use that energy up, and if you keep going beyond the time you use that up, you need to be in charge sustaining mode, which means you're using both the engine and the motor together anyway, so you still need to be thinking about this stuff. In a battery electric vehicle, it doesn't apply because there's no engine. So, but just one last thing. So if you have a plug-in hybrid vehicle, though, where you're charging the battery up, you would probably have a different strategy where you try and want to use all of the energy from the wall first, or mostly first, before you get into a charge sustaining mode like this. Yeah. Yeah.
Maybe something a little bit more about why the government supplied drive profile didn't reflect real driving.
Just because that's the way they defined it. They defined it. That profile has been in place for a long time. Back when cars weren't as powerful as they are today, and people didn't drive as fast as they do today, when speed limits were 55 miles an hour. So it represents a different time than we have today, and they haven't updated. They have made other kinds of changes, though. They have about maybe 4 or 5 years ago, they made a change where they now have an adjustment factor. So they're recognizing the fact that it underperforms, that the vehicles underperform the actual mile per gallon on the label. They have an adjustment factor to just artificially lower the fuel economy from the test. Okay, so that's why I showed you numbers that were like 75 miles per gallon and stuff. That was an unadjusted number. And so once you adjust it down to label level, it's more realistic. So, yeah.
Can you comment more on the relationship between the complexity of the control system and the cost of electrification?
Oh, well, they're related. So, right. So, I mean, the control systems in the vehicle now are so complex that there's no way that we can verify every aspect of the control system. So the way we decide which aspects we're going to verify are by doing failure mode effect analysis, where we look at potential categories of failures of the system, and anything that would impact safety, of course, or regulatory requirements, or would be a major dissatisfier or something. We verify all of that. Things that might, and we have to draw a line somewhere because we just can't verify every last line of every code. So things that, functions that wouldn't be a major dissatisfier would just be a minor dissatisfier, they may not get verified, right? So I guess you gotta sort of pick your battles. Yeah.
I enjoy driving my manual transmission car, which I think gets me some more fuel mileage. But
Yep. Well, not everybody does, but I'm glad you like it.
But, is there some analog manual transmission that could be used in these, and could you learn from someone driving it, or is it just humans aren't going to be able to do that anymore?
Oh. I think you'll be able to have a manual for a while.
Would I be able to shift to the turn the electric on, or how?
Well, okay. So once you.
What would I be doing with my stick shift?
Yeah, I mean once. Yeah, we don't have any plans for hybrid manuals because because you'd mess it all up.
Maybe I'd be really good. You could.
So in a conventional, so just to sort of put it in my terminology here, in a conventional automatic vehicle, or any conventional vehicle, you have 1 degree of freedom. So the hybrid vehicle I showed you have 2 degrees of freedom, right? We chose battery-powered, engine speed, or whatever we chose. In a conventional vehicle, you have 1 degree of freedom, just by the kinematic arrangement of the vehicle. And that degree of freedom is gear. So you can choose your gear that you're going to be in, and that'll move your engine operating point around, and that's your degree of freedom for choosing fuel economy, right? So now if I build a hybrid manual and let you choose the gear, right, you're going to really mess up the energy management strategy probably. Or maybe you're good, but I'll trust my control system.
I have a question.
Yeah.
So all through the talk you have this thing about balanced attributes.
Yeah.
But if you have the right architecture, does that not become not important? Because if you have the right architecture, these things are decoupled in a way that you can optimize one thing.
Yeah, you can't. Yeah, no, you can't. There's a lot of requirements, attribute requirements that you cannot decouple. I mean, so for the obvious ones are maybe performance and fuel economy, just the basic 0 to 60 performance versus fuel economy. If you insist on having a 7-second 0 to 60 time, but you want to hit 50 miles per gallon, that's going to be pretty tough to do. Right? But if I want a 20-second 0 to 60 time, I can probably build you a 50 mile per gallon vehicle. Right? Just make it really, really light and small engine, and you get 50 miles per gallon, but it won't accelerate very fast. So some of the stuff is just physically impossible. Right? So, yeah.
One question on sort of the attributes. So something like that, where there are enough people who care about having a very fast vehicle, they're going to be upset they can't accelerate fast. I think there might be a lot of other people, maybe particularly today, given how the price of fuel is going, that would be okay with it, that don't care about having as large of an engine. Of course, the second you downsize your engine, your fuel economy is going up.
Yeah.
So what Ford's sort of attitude right now, I'm curious, is in terms of maybe changing rather than or modifying some of the attributes I think has been sort of the norm in the U.S. or in sort of societal culture here, but that maybe are changing. And what do you think is your role in changing? Do you think that you have to wait for the customer to demand it, or do you think Ford has a role to play in saying we're going to actually create some vehicles that don't have some of those power attributes, but are very good?
Well, I think so to answer, I think it's very hard for Ford to tell people that, you should drive this instead, because people can drive what they want to drive. Right? So, I mean, I think a lot of people can say what they think is important, but at the end of the day, people make their own decisions, right? That being said, though, so we have a new boss about 2 or 3 years ago for Ford, the CEO, and he came in, and I think he recognized that we were going the wrong direction on fuel economy. And so he has really taken some strong steps to change that, and it was really accelerated by the fact that gas went to $4 a couple of years ago. So now a lot of our investment is in small cars. It used to be, so Ford Motor Company was a truck company, SUV company, and I don't know what percent, but I don't know, maybe 70 or 80% of our investment went into those kind of cars. Now our targets are more like 50-50, that we're investing heavily in cars, including small cars. We're releasing, in about a month or two, we're going to be introducing in the United States the Fiesta, which is a B-size car, which is smaller than the Focus. Okay, so that's a big step for Ford to bring that car to the United States. We're also introducing a new Focus this year. There's a couple big cars. I'm trying to think. And there's Focus, Fiesta. One other car we're introducing this year, I can't remember. But anyway, so we're investing heavily in cars now, especially small cars as well. So we're trying to make them available, and it's up to the customers to buy them, right? So, yeah.
Well, most of the projects I think for all the projects that you showed, like they all were not very robust in general. So I'm just wondering, like, how well suited do you think the world of academia is to practical industry, and do you see like a large role in the future for academia, or would you say that most of the design of cars is going to be just like more common sense approach and maybe less sophisticated approaches?
Well, okay, so there's always a role for academia. I mean, I think you guys, the people in places like this are some of the brightest minds that come up with some great ideas. And one way or another, those ideas eventually get into products, whether it be cars or something else. But I think it's very difficult for somebody in academia, not knowing that entire process and what all of those concerns are throughout that process, to design something that's going to be dumped right into the car. So I actually feel pretty happy about all of these projects we're working on, that we've been able to influence them in a way that makes sure that what they come out with has a roadmap to implementation. So for instance, on that first one, the model predictive control, I went back and forth with the professor a few times. He wanted to use more loose assumption, or more, he wanted to assume that he knew more about the driver's future drive cycle than I thought was warranted. I insisted that he assume as little as possible about that to make it more implementable. So it's more realistic. And he was open to that, and he appreciated that and understood why I wanted that. And so I think by having a good collaboration, you can help make sure that the assumptions are realistic and that there's some roadmap to realization. Yep. So.
Yeah, thanks, speaker.
All right. Thank you.